Okay, as I said, we will return in more detail to climate and human evolution in the next chapter, but I wanted to touch on it here just in terms of the evidences that have to be combined, all the hominin fossil and tools and other things, stone tools and so on, have to be combined with climate, and I just wanted to raise some of the points. So you find various such figures. This one is looking at the Pliocene-Pleistocene climate transition illustrated by the increasing benthic delta O18, which corresponds to ice volume. If you don't know how O18 and isotopes in general work, you can refer to my podcasts in other courses on my channel. Essentially, it corresponds to how fractionation happens during evaporation and precipitation, and how that leaves a signature in benthic delta O18 that corresponds to ice volumes or cold climates. And the sea surface temperature cooling in the Benguela upwelling system off of southern Africa, and the alkanone-based atmospheric CO2 decline. So these are various paleoproxies, and I have podcasts on paleoproxies as well. So here is time going from about 5 million years to the present, and we are looking at the onset of major northern hemisphere glaciation here. So basically the climate variability shifted from higher frequency but smaller amplitude 41,000 year time scale, which corresponds to the obliquity. Again, if you don't know how orbital time scales and Milankovitch cycles work, you can follow up on my other podcasts. So there was a warm Pliocene epoch, and it switched to Pleistocene around this time, where the amplitude of the variability as recorded in the benthic delta O18, which correspond to warm and cold climates, went up, and the frequency decreased, became 100,000 year time scale, glacial deglacials here, with some mixed time scales before that. There is corresponding sea surface temperature evidences, and you can see there is a general drift from warmer temperatures here towards colder temperatures. You don't have to necessarily worry where these particular cores come from, but in general this corresponded to global changes. And of course there was changes, corresponding changes in CO2, because warm deglacial times correspond to higher CO2, and as glaciation happens, CO2 tends to reduce. So when we came into the pre-industrial revolution timescale, we were at 280 ppm or so, and of course with anthropogenic activities we have now brought it to about 420 ppm or so. There is a much longer context to this, again looking at deep ocean temperatures and delta O18. We can go back to the time of the dinosaurs when they went extinct. Temperatures were up here compared to where they are at present in terms of deep ocean temperatures. And there was the Paleocene-Eocene thermal maximum, which was a spike in temperature, and one of the largest spikes in the record over this time period, but it turns out to have happened slower than the global warming we are having here, which you cannot see in this particular plot. But you can see that there's been a general trend towards cooling over the last 55 million years or so, and the human evolution and global warming are happening in this context. So we are talking about lower resolution as you go back in time in terms of the reconstructions, but you can see the mid-Eocene climate optimum here, the 011 glaciation that shows a cooling, and then there is the mid-Miocene climate optimum, and then a more rapid cooling here. We'll keep zooming into these time scales, but the Antarctic ice sheet began to grow somewhere around here. The northern hemisphere ice sheets began to grow here in the Pliocene-Pleistocene boundary, as we talked about before, and the rise of the Himalayas happened here, and drawdown of CO2 happened, which is one of the leading hypotheses is that Himalayas rose and monsoon began to set in. All the material that was brought up began to be weathered, and that led to accelerated weathering and drawdown of CO2 and this global cooling in general. Okay, so here you can see in terms of delta O18 again and temperature, this is another way to look at it. So you can just keep this in mind. Here you can see again the various time scales, but if you zoom into the last few million years, again global deep ocean temperatures past 5.33 million years, you can see more clearly the change in the time scale going from obliquity dominated time scales in terms of delta O18 recorded temperatures and the 100,000 year or ellipticity driven time scales during the Pleistocene, especially in the last 1.8 million years or so. And if you zoom further in to the last 800,000 years, you can see these glacial cycles, the rapid warming of the deglaciation and the slow cooling during the glaciation. As glaciation sets in, the albedo begins to increase because glaciers reflect a lot of sunlight. Atmosphere gets drier because it's colder, and that reduces the snowfall rate, so glacier growth rate slows down. Whereas in the warming phase, as we are now in the global warming, glaciers retreat, albedo decreases, more energy is trapped, warming happens, more glacier retreat happens. So there's a positive feedback in both phases. One goes very fast and can lead to abrupt changes, other one goes slower, and so on. And you can here recognize the Holsteinian, Eemian, and Holocene. So we'll focus much more on this as the time when the Homo sapiens arose, and then Holocene jumped up here at the end of the last glaciations, which reached its maximum around 21,000 years ago, and who have had fairly stable climate during which most of the humans evolved. That's the context. The other big change that happened during this time is, if you look at the position of Australia and New Guinea 3.54 million years ago, there was a different connection between the Pacific Ocean and the Indian Ocean. So you can see how the exchange happened between the Indian Ocean and the Pacific Ocean. But if you look at 3.3 million years ago to the present day conditions, you can see that the exchange changes quite rapidly. So this northward movement of Australia and New Guinea at about 3 centimeters per year is still going on. So everybody is moving north right now. So that blocking changed the connection and argued to have changed the climate over East Africa as well. So in today's normal climate, we have upwelling and cold temperatures around Galapagos, warm temperatures here, the so-called warm pool, cold tongue contrast with 8 to 10 degree sea surface temperature gradient. During the Pliocene 3 to 5 million years ago, there was a so-called permanent El Nino where the temperature gradient was much flatter. What happens now is, once in a while when El Nino happens and this temperature gradient gets flattened like during this permanent El Nino, then there is rainfall over East Africa, anomalously high rainfall over East Africa. So the change from this condition to this condition changed the vegetation over East Africa from lush green forests into savannas and grasslands as it exists now. That's what is called East African aridification, and that's argued to have led to bipedalism, as we'll see in a minute. But there is a debate about whether this was really a permanent El Nino and whether the conditions before that in the warmer Miocene-Pliocene state were much more of a contrast as well. So maybe this permanent El Nino was not so permanent according to this, because this also has an east-west temperature gradient like here. So this is a separate debate, but if you look at the links made, again going back in time to the time of our ancestors, the great apes, and then the beginning of the Australopithecus ramidus, and grasslands and woodlands changes in East African soil carbon as seen in the delta C13 signatures. Again, C13, C12, another fractionation story that you can look up in my other podcasts. But you can see the speciation from Australopithecus afarensis that we talked about before. The Homo lineage evolves, Ruralfensis habilis, Rectus, and Sapiens. Neanderthals are missing, but you know how that goes. There was coexistence of some of these ancestors, hominins, in terms of Africanus, Paranthropus Ethiopicus, Paranthropus robustus, Boisei, and so on. So they all obviously went extinct, and our Homo relatives also went extinct, and we are the ones standing now. So you can see here the transition from woodland to grassland around this time, and a more record of temperature change recorded in benthic delta 018 shows interglacials here, obliquity period at 41,000 year dominating 41 kilo year time scale here, and the 100 kilo year ellipticity time scale, glacial interglacial periods. So this hypothesis about whether climate played a critical role in our evolution, so here 23 to 19 kilo years, so that's more of a precession time scale, obliquity time scale, ellipticity time scale, and whether these speciations and the extinctions and so on are related to climate, ability to deal with climate change, resource limitations either caused by climate change itself or the response to climate change, whether it's extinction of megafauna and flora and so on. All questions remain, of course, not completely answered, but one cannot ignore the fact that climate may have played a critical role in our own evolution. And you can zoom in to the last last million years, where the glacial deglacial cycles at 100,000 year timescales have happened, and without going into details, glaciation and deglaciation are also associated with changes in methane and CO2 and N2O and so on. You can see the relations is very strong. Of course, temperature change happens first because it's orbitally driven radiation changes that lead to melting or growing of glaciers, and that leads to changes in precipitation, winds, dust, biological production, carbon uptake by the ocean, vegetation on land, and so on. So obviously vegetation changes are also a part of this story. So what is the resource limitation, whether that's related to megafaunal extinction, human response to resource changes, climate change driven changes both on humans or hominins and fauna and flora and so on, are very complicated questions. So the relative sea level changes along the way as well, but here we are zooming into the last ice age starting around 130,000 years ago and ended about 18,000 years ago, and sea level rose back. So how did sea level change affect the various things, including the diaspora that we are talking about on these time scales? Because each time there was glaciation and deglaciation, sea levels would have changed like this, order 120 or more meters. That would have changed, as we saw before, shelf areas and migration paths and so on and so forth. Okay, this is just zooming further in, looking at the last 80,000 years. There have been millennial timescale variations, marine isotope stages, Danskar-Ushker events, and so on, that we'll come back to. And there are also rapid changes that happened during the modern Holocene warm period, and one thing to remember is that our ancestors lived through these large changes, whereas modern humans have basically evolved during this relatively stable period that was associated with relatively stable sea level changes as well. So you can see again these glacial deglacial changes happening here. I won't go into the details, but there are uncertainties in climate reconstructions themselves, and explaining the climate variability is also full of hypotheses, which means not a single robust accepted theory. So here are some ideas about salt oscillator hypothesis during the warm stadials and cold stadial conditions, which have to do with the so-called meridional overturning circulation in the ocean. So you can see the Laurentide ice sheet and the Fenno-Scandinavian ice sheet and ocean sea ice extending far down into lower latitudes during the warm stadial interstadials and the cold stadial conditions. So the extension and thickness of ice and so on change. Whether that is related to how meltwater affects the deep water formation here and the overturning, or whether that's also related to changes in wind field oscillations is not clear. As I said before, when you have multiple hypotheses, it generally means that we are still trying to find a proper or acceptable single explanation. There is no reason that only one process happened anyways, but nonetheless it's also obvious that winds and salt are related, in the sense when winds change, when ITCZ moves, rainfall patterns, evaporation patterns change, so salt distribution changes, its transport by the ocean circulation changes, and that interacts with the meltwaters from the ice sheets. So ice sheet growth and melting themselves change because of precipitation distributions and so on. So the overturning circulation and wind-driven circulation are not necessarily independent of each other, but let's leave that for another time. And just giving you a brief idea about how reconstructing climate itself brings in a lot of uncertainties, then trying to relate it to human evolution and especially the diaspora. As we saw from the results of Axel Timmerman, he goes into low resolution climate simulations that are continuous for long times, which has some advantages in the so-called transient simulations, which he uses to argue about the relation between out of Africa migrations and speciations elsewhere, let's say from Heidelbergensis into Neanderthals, Homo erectus, Homo habilis, Homo sapiens, and so on. So we'll have to just leave it there, in the sense that climate definitely seems to be a key player, but it may not always be the ultimate cause, it may not be necessarily the proximal cause, the immediate cause that drives diaspora in this context that we are discussing, but it may be an ultimate driver in the sense of affecting the flora, the fauna, the pathways, the sea levels, resource limitations, and so on, and drive diaspora. So uncertainties are there in each of those components. So we'll come back and look at one example of how multiple evidences are combined to figure out how megafaunal extinctions may be related to climate or hunters and gatherers. Okay.